Welcome everyone to this presentation, which will be about learning optimal intrusion responses via decomposition. My name is Kim Hammar, and this is joint work together with Professor Stadler at KTH. So we consider the following use case. We assume that we have an IT infrastructure that you see here to the right that consists of a set of connected components which jointly provide services to a client population. This infrastructure is operated by an organization that we in this context refer to as the defender. The defender can defend the infrastructure by a combination of monitoring the network to detect possible attacks and also actively taking decisions to respond to ongoing attacks. In addition, there is an attacker that seeks to intrude on the infrastructure and wants to compromise components. To achieve this, the attacker uses reconnaissance to gather information and discover vulnerabilities, and then it has to exploit those vulnerabilities in order to gain access. And we study this use case from the defender's perspective, down here, and our goal is to find automated strategies that the defender can use to respond to intrusions in real time as they occur. This is a long-standing goal in cybersecurity, where we are trying to, as much as possible, automate the response to cyber attacks so that we can reduce the response times. And one promising approach that is actively investigated currently is whether we can utilize decision theoretic and learning-based methods to achieve this automation. And that is the topic of my presentation today. To investigate this, we have developed a general framework that you can understand on a high level through the following picture. The starting point here is that we have a target infrastructure, and that corresponds to the infrastructure that we want to defend. So this is where we want our defender strategies to be operational in the end. The first step of our method is then that we take the configuration of this infrastructure and we emulate it to create a digital twin, so a virtual replica of the real system. We then use the twin to run experiments where we investigate the performance of different responses against various types of attacks. And based on the data from these experiments, we then perform system identification to identify a formal model of the system. This could be, for example, a game theoretic model or a Markov decision process, or perhaps a dynamical system of some sort. Once we have that model, we can then formulate an optimization problem for finding the optimal defender strategies. And to solve that problem, we apply numerical methods like reinforcement learning or dynamic programming or other optimization techniques. Finally, once we have computed these strategies and solved the problem, we can extract them from the simulation environment and evaluate them in the digital twin. And if this evaluation is deemed successful, we may also implement the strategies in the target infrastructure. So that is our overall framework on a high level. And in the remainder of this presentation, I will go through the different steps here in much more detail. So the first part of the talk will be about how we create the digital twin. And this part will really be quite practical about systems. Then the second part of the talk will be about how we use the twin to optimize our defense. And this will be much more mathematical. So the input to our framework in creating the digital twin is a configuration file that defines the infrastructure. So this includes everything from the components of the infrastructure, the topology of the network, the services, the vulnerabilities, the user accounts, etc. And we can think about the set of all of these configurations that the framework supports as defining a configuration space, so that any digital twin that we create corresponds to a particular point in that space. Throughout this talk, I will focus on one such configuration, which is the one that we see here. So this is an infrastructure with 64 nodes that are connected in the topology that we see to the right. And the first step in creating a twin of this environment is that we have to emulate the physical nodes. So we have to emulate the servers, the switches, and the gateways. We do this using virtual containers. So we map each physical node to a container and then we run software inside that container to emulate the processes and the services offered by the component. Once we have created all of these containers to emulate the physical nodes, the next step is to emulate the connectivity among them. And we do that using virtual networks. So we create virtual subnets using network namespaces that we can attach the containers to. And then we connect these subnetworks into an overlay with the VXLAN. And that overlay is typically then running on top of a substrate IP network. Furthermore, when we create this overlay, we also want to make sure that this network, the emulated network, should resemble the real network that we're trying to emulate as much as possible. And we achieve that using the netdem module in the kernel, which allows us to configure things like bitrate, packet loss, delay, jitter, and so on. So we can then use our knowledge about the real network and configure this emulated network accordingly. Finally, the last step in creating the twin is that we have to emulate actors. So recall that we want to use the twin to investigate what are effective response strategies against various types of attacks. So to do this, we clearly need to emulate the responses, the defender. We also need to emulate the attacks, the attacker, and we need to emulate clients so that we can measure what is the effect on the service of the system based on the responses. To emulate clients, we use a Poisson arrival rate, and then we have load generators to generate requests that the client send to the infrastructure or the services. To emulate the attacker, we utilize pen testing tools like Metasploit and Nmap to create automated scripts for attacking the system. And finally, to emulate the defender, we have developed a custom API which allows us to automate common blue team operations like migrating nodes, updating firewalls, certificates, flow tables, and so on. So that concludes the first part of the talk in how we create this digital twin. The next step now will be about how we can utilize this environment to optimize our defense. So this is the outline for the remainder. So far I covered the use case and the digital twin. Next, I will detail our system model, which is based on a game theoretic formulation. Then the core of this talk, and also the main contribution of this work, is how we can decompose that system model to enable efficient learning of defender strategies. And then I will show some preliminary results of evaluating those strategies in a virtual infrastructure. And then I will conclude and provide some pointers for future research. So we model the target infrastructure as a directed graph. The nodes in this graph correspond to virtual components. And following best practices, we assume that nodes are by default isolated in the network, and only if they can have some dependency can they communicate. And we model these dependencies with edges in the graph. We further consider that the infrastructure is segmented into different zones, each of which has its own access control policy, and every node is part of one zone. But that zone may change over time, which we model with the state of the node, which is a vector with 3 components. So we have the zone, the intrusion state, and the reconnaissance state, which determine if the node has been compromised or discovered by the attacker. The complete system state is then the concatenation of all of these vectors, which we denote with S, and that is a realization of the random vector, capital S, which is dynamic in the sense that it evolves over time according to a transition function F. The nodes in the infrastructure run services that are connected into what we call workflows. And here a workflow is simply an abstraction that we use to model a set of nodes that are dependent in some way. So this could, for example, be a chain of microservices that provide some web service, or it could be more general than that. It could also just be a general purpose compute cluster, for example, like a Spark cluster. Just any set of nodes that have interdependencies. We capture these workflows in the model as directed acyclic subgraphs of the infrastructure graph. And this leads me into our main assumption in the model, which is that every node is part of exactly one workflow. And I claim that this is without loss of generality, because if you want to model a node that is part of many workflows, you can always do that by just splitting up the nodes into many smaller ones, each of which is only part of one workflow. And it just turns out to be very convenient to have this assumption, because it means that the set of workflows induces a partitioning of the set of nodes. So that cal v here is a non-overlapping union of cal v subscript w, where w is the workflow. And I will utilize this property later on to prove a theorem related to the decomposition. The workflows are consumed by clients that arrive to the infrastructure with a Poisson rate, and will then select one of the workflows and start sending requests to the services. And they will keep doing that until their service time has expired, and then they will depart. And we model the service times here with an exponential distribution, as is common practice. So these client interactions, in combination with the attacker, generate a lot of traffic on the network, which the defender observes through intrusion detection systems here that inspect the traffic and generate alerts. And we capture those alerts in a model with these vectors OT, where each component of OT contains the number of alerts for a given node at a given time. We consider that these vectors are distributed according to a joint distribution Z. We don't really know what Z looks like. We just assume that Z exists, and we can estimate it from data. And here are some empirical distributions of Z. So one distribution for each node in the target infrastructure. So we have 64 nodes and 64 distributions here. I have aggregated the distributions so that in red you see the distribution during normal operation, and in blue you see the distribution during an attack. Y-axis shows the probability and x-axis shows the number of alerts. So the first thing we can note is that there's a lot of false alarms. That's why the distributions overlap. But even though there's false alarms, we see that on every node there is some signal for detecting an attack. And even though this signal varies in strength. So for example, on node 17 here is a quite clear signal. There's a big difference in distributions. Whereas on node 24, the signal is much weaker. We estimated these distributions here using data from the twin. So in the twin, we have the following monitoring setup, where every emulated device run a monitoring agent that collects metrics and log files and other data periodically, and then pushes that information to an event bus, which then is consumed by data pipelines that process the data and write it to storage systems, both for historical data aggregation, but also for real-time decision-making. And using this setup, we collect hundreds of metrics at every time step for every node. And among those metrics, we find that the intrusion alerts provide by far the most information for detecting the type of attacks that we consider. So that's why we focus on just this metric in our model, to keep the model small, because it provides the most information for the defender. And we measure the information here by taking the KL divergence between the distribution during attack and during normal operation. Okay, and based on these observations then, the defender has to make decisions about which defensive actions to take. We define a defender action to be a vector, where each component in its vector contains a sub-action for a given node. That sub-action can take on 5 different values. 0 means to do nothing and just wait, and 1 to 4 correspond to defensive actions, which are illustrated to the right. The first defensive action is to do node migration. So this is a good action, for example, if the defender suspects that a node may have been compromised, but you're not really sure, then you may want to migrate that node to a demilitarized zone temporarily in order to investigate it. Second defensive action is to migrate or block flows in the network. So the defender may block flows based on IP. It may also migrate flows to a honeypot, for example. The defender can also take more draconic actions and may decide to shut down a server or to revoke certificates of a server. Naturally, these actions also come with a higher cost for the defender. In deciding between which actions to take, the defender considers the entire history of observations, so not just the latest one, since the latest one will not be a Markovian signal. So we therefore define a defender strategy to be a mapping from histories to actions. And in designing this strategy, the goal of the defender is to balance two objectives. So on the one hand, it wants to maintain workflows to its clients, and on the other hand, it wants to quickly stop a possible attack. And as you may realize, these two objectives are actually slightly conflicting. Finally, we define the attacker model in a very similar way. Just like the defender, the attacker selects an action at every time step. That action is a vector, where each component corresponds to a sub-action for a given node. And the sub-action can take on 4 different values. 0 means to do nothing, and 1 to 3 correspond to offensive actions. The first offensive action is to do reconnaissance and scan the node. The second one is to do a brute force attack. And the third one is to do a code execution attack. Each of which has some probability of success depending on which node you apply it to. So if that node is vulnerable or not, for example. Just like the defender, we define an attacker strategy to be a mapping from histories to actions. And we model the objective of the attacker to be diametrically opposed to the defender. So that the attacker not only wants to to compromise nodes, it also wants to disrupt workflows and deny service to clients. Finally, now, based on these definitions, we can now formally state the problem that we're trying to solve, namely the intrusion response problem, which is defined here in equation 1. Implicitly, what the equation 1 is defining is a game where the maximizing player is the defender and the minimizing player is the attacker. This is a particular type of game called a partially observed stochastic game with public observations that I will denote here with capital gamma. And having now formally defined the problem that we want to solve, we can now start analyzing it and see how can we obtain a solution. And the first thing we can do, the good news, is that we can show that equation 1 here has a solution. So in other words, the game has a value and a mixed equilibrium exists. So that is the good news, that a solution exists. Unfortunately, the bad news is that even though the solution exists, computing it for any non-trivial instantiation of the game is intractable. And the reason for this is that the spaces of the game, so the state, action, observation spaces, grow exponentially with the number of nodes. So as you can see in the plot here, if you have 1, 2, or 3 nodes, you can probably solve the game. But even with only 4 nodes, you run into this combinatorial explosion, which makes the game intractable to solve. This is clearly a big challenge for us because we are looking at an infrastructure, a target infrastructure, with 64 nodes. To tackle this challenge, we propose a decompositional approach, and that is our main contribution that I will talk about next. So before I dive into the theory here, let me just give you the main intuition, and that is that the high computational complexity of the game stems from the interconnectivity among all of the nodes. That is what causes this combinatorial explosion and the very high dimensionality of the game. But intuitively, if you think about it from a defender perspective, the optimal defensive action we select for a node up here should not directly depend on the optimal action down here, even though they are connected in some sense. So they're not completely independent, these two decisions, but it turns out that they satisfy there's a certain type of conditional independence here that we will exploit so that we can isolate certain decisions from each other in the network and thereby break this very high dimensionality. That's the idea. And I will do this in 3 steps. So first, I will show that the game can be decomposed on the workflow level into a set of additive subgames that we can solve independently and then combine. Then I will show that each of those subgames can also be decomposed on the node level into subproblems that are not independent, but they satisfy the optimal substructure property. And finally, once we've done this decomposition, we will see that when we have the local problems, there exists an efficient algorithm for solving the local problems that utilizes certain threshold structures of the problem. And I will go through it in a top-down way. So we start with the highest level of decomposition, which is on the workflow level. So the idea here is that if you have 2 nodes in the infrastructure for which there's no path in between them, then they are independent in the following informal sense that I will make formal on the next slide. So if the attacker attacks one of the nodes, first of all, that will have no impact on the state of the other node. And I think this should be very clear because there's no reason, if I run a command of one node, why that would change the configuration or the state of a completely different node. The second thing, which is not as clear, but it's also true, is that if the attacker is successful in compromising the node, it won't make it any easier or harder for the attacker to reach the other node. And that is because there's no path in between them. And by a similar way of reasoning, if the defender defends one of the nodes, that will not impact the service or the state of the other node. So more formally, we're talking about 2 types of independencies. First, we have what we call transition independence, and we say that a set of nodes are transition independent if we can factorize the transition probability like this. In other words, if the local state of each node is conditionally independent of the other nodes, given that you know the local state in action. Then we have utility independence. So we say that a set of nodes are utility independent if we can take the utility function and rewrite that as a function of the local utilities, which is such that if you maximize the local utilities, you also maximize the global utility. If that is the case, then we say that they are utility independent. Now, if you have 2 decision problems, say the problems of selecting response actions for 2 different nodes in the infrastructure, then if they are both transition and utility independent, then they are completely independent, and we can solve them in parallel and then just combine. So that is what we want to have. And it turns out that in our game, all of the nodes are actually transition independent. And I claim that this is a property that holds for many infrastructures in practice. Secondly, we can also show that if there is no path in between 2 nodes, then they are also utility independent. And a very useful corollary of this is that since the workflows in our model by assumption satisfy this isolation, there are no paths in between 2 workflows. Therefore, we can decompose the game on the workflow level into a set of additive subgames, 1 per workflow. And we can then solve these subgames independently and in parallel. So this is what I've tried to illustrate here with a block diagram, where in each block you see a workflow strategy that we can optimize independently. That produces a workflow action, which is a vector, with we have 1 sub action for each node in the workflow. Then to obtain the globally optimal action, all we have to do is to concatenate them, which I denote here with this circle symbol. And this concatenation is always possible due to this assumption I made earlier that the set of workflows partitions the set of nodes so that these vectors will never overlap and we can always concatenate them. This result can also be understood with more graphical models. So here we have a minimal example to the left. It's an infrastructure with just 3 nodes, where 1 and 2 are in the same workflow, and the 3rd node is in a separate workflow here. In the graphs here, the circles correspond to random variables representing the state, action, observation, and utility variables. And the edges correspond to dependencies. So what you want to look for in these graphs is actually the lack of arrows, because that implies independence. And using this language of graphs, we can say that transition independence across nodes means that we can group the state variables per node, and there should not be any arrow crossing the node boundaries. If there's no such arrow, then we have transition independence across nodes. Similarly, if we can group the utility variables per workflow, and there's no arrow crossing the workflow boundaries, then they are utility independent across workflows. And I think the utility independence here is the most interesting. So if you look at it here, you see utility of node 3 depends only on the local state and action of that node. On the other hand, the utility of node 2 depends on the local state and action of node 1 and 2. And this is actually very natural, because if you look at the infrastructure graph, you see that if I put a defensive action on node 1, say that I block it or I shut it down or something, that will then block the traffic coming to node 2. And that will impact the service to node 2 and also the safety, and therefore the utility. So they are clearly utility dependent. On the other hand, if I block node 1, that will have no impact on the traffic to node 2, and therefore they are actually utility independent. So that was the first step of the decomposition, where we've shown that we can now decompose the game into a set of additive subgames, one for each workflow. The final step now is to show that we can decompose each of those subgames into subgames on the node level as well. This step is a little bit more tricky because the nodes in the same workflow are not independent. They are utility dependent. This means that we cannot just expect to take the local solve the problems, the local problems, solve them in parallel and then combine. That won't work. It won't be optimal. But it turns out that the local problems satisfy a property called optimal substructure, which means that there exists an algorithm for combining the local solutions into a globally optimal solution. And that algorithm is given here. It's actually a very simple algorithm, but I know that reading pseudocode on slides is usually not very easy or pleasant, so I will go through it with an example. Here we have an example workflow graph. The circles correspond to nodes in the workflow, the edges correspond to dependencies, and the symbols inside each circle corresponds to the local strategy for a given node. And let's assume now, for the sake of the example, that we have already solved the local problems, so that the local strategies are optimal locally for defending each node. And our task now is to have an algorithm for combining the locally optimal strategies into an action that is optimal for the entire workflow. And to do that, we will consider the nodes one by one in a topological order, and then sequentially build up an action for the workflow. There are several such orderings, but we can pick any one of them. So we can, for example, start from this node. And it turns out that since this node does not have any parent in the graph, the locally optimal action is actually the best thing to do. So we're just going to pick that action. Then we move on to the next node in the order, which is this one. Same thing here, it does not have any parent in the graph. So the locally optimal action is the best thing to do, and we pick that action. Then we move to the next node. Here something interesting happened. So based on the action that we selected for this node, the topology changed. So these two arrows disappeared. That may, for example, be the case if we shut down that node or if we updated the firewall, for example. And now we see that the next node that we consider, this one, is actually isolated from the rest of the network. So there was only one arrow coming into this node, and that arrow is now disappeared, which means that the attacker cannot reach this node. And therefore, the best thing to do for the defender is to pick action 0. So you don't need to defend a node that is not even reachable to the attacker. An important thing here is that we're going to pick action 0 for that node, even though the locally optimal strategy may tell us to do something different. And this is because we now have this global perspective where we know what the other neighbors in the graph are doing, and therefore we can pick action 0 here. We can conclude that that is the best thing to do. And then we continue to the next node in the order, which is this one. And now for this node, this can now be considered as a root node in a subgraph, because we have already considered all of the parent nodes here, and we have updated the graph. So we know that this guy did not do anything that changes the incoming traffic to our node. We still have this arrow here. So that means that we can actually show that the locally optimal thing to do for this node is actually the best. So we're just going to pick the locally optimal action. And then we continue in the same way. We update the graph, move to the next node, same thing. And in summary, the algorithm is as follows. We consider the nodes in the topological order. We pick the locally optimal action, update the graph. If any node became unreachable, pick action 0. Otherwise, continue down the graph. And the result of all of these steps is then a vector here, which is an optimal workflow action. So now you may wonder, why do we complicate things? Why do we started out with just a single game. Now we have many subgames. And we also have this extra algorithm that we have to use in order to combine the solutions. But the big benefit is that even though we now have many sub-problems, solving them is significantly easier than the original problem. And we can also solve them in parallel. Furthermore, the number of sub-problems we have to solve grows only linearly with the number of nodes. So we don't have this exponential growth anymore. In the plot here, you see the space complexity of the original problem and the decomposed problem. So the y-axis shows in log scale the complexity, and the x-axis shows the number of nodes. The lines here, they illustrate the exponential growth in the complexity of the original problem. And the constant lines here, they show the complexity of the fully decomposed problem. So as you can see, even when you have a very small number of nodes, there are several orders of magnitude difference in the complexity of the problems. So that is the big benefit of the decomposition. Finally, we have now seen that we can decompose the game. We have a lot of these sub-problems, and we have an algorithm for combining the solutions into a globally optimal solution. But what we haven't seen yet is how do we solve the local problems? And that's what I will cover now. So the first thing I investigated was, can we utilize dynamic programming to solve the local problems? Because they are so small, so maybe it's possible. And unfortunately, it's not the case. So even though the problems are small, the local ones, they are still partially observed, which means that obtaining an optimal solution with dynamic programming is p-space complete. And that is in general not tractable. So the size of the local problem depends on the number of observations, the observation space, and the number of zones. And you see that even for very small configurations, the execution time just explodes. So dynamic programming is not feasible for the local problems to solve it. It's not scalable. Which means that we have to use some approximation techniques. And this is where reinforcement learning becomes very useful. So here, I have applied the deep reinforcement learning algorithm, PPO, to the problem. In the top row, you see the performance when I optimize the defender against a static attacker. So we're learning best responses. In the bottom row, you see the performance when I optimize an attacker against a static defender. If you focus first of all on the top row, you see in the red curves, the performance in a fully decomposed game. In the blue curves, you see the performance in the game decomposed on the workflow level. And in the orange curves, you see the performance in the game, in the original game that has not been decomposed at all. And what we can see is that the red curve has a very nice scaling. So as we increase the size of the infrastructure, the convergence rate remains basically constant. On the other hand, the convergence rate for the blue and the orange curves just gets worse and worse as we increase the size of the infrastructure. And we see a very similar pattern in the bottom row, where the purple curve shows the performance in the fully decomposed game. The brown curve shows the performance in the game decomposed on the workflow level only, and the green curve shows the performance in the original game. The reason why we have this nice scaling when we use the decomposition is that we can parallelize the solution to the subproblems. So this gives us very close to linear scaling, which is the best thing that we can achieve. Okay, so we have seen now that we can solve the local problems with deep reinforcement learning. That works. It's quite efficient as well. But it turns out that we can optimize this a little bit more, and we don't need to use a complicated deep reinforcement learning algorithm. At least for the defender, we don't need to do it. We can use a much simpler and more efficient algorithm. And the idea is that we can utilize some intuition about what is the problem for the defender and what actually are the main tasks. And when you define a local node for the defender, it essentially involves two main decisions. The first thing is that you have to decide when to take a defensive action. And the second one is to decide which defensive action to take. And deciding which defensive action to take is actually a fully observed problem that we can solve very efficiently with dynamic optimization. And the problem of selecting when to take the action, that corresponds to a partially observed stopping problem, whose solution is characterized by a switching curve that can be estimated very efficiently. So more specifically, the local state of a node, attack state, can be in three different values. It can be healthy, it can be discovered by the attacker, or it may be compromised. The defender does not know which one of these we're currently in, but it can form a belief about the current state. And that belief is a probability distribution over the state space, which resides in a two-dimensional unit simplex, which is this triangle that we see here. And it turns out that there exists a switching curve that partitions this space into two regions. One region where it is optimal to continue, the shaded region, to not take the defensive action, and another region, the white one, where it is optimal to take the defensive action and stop. And this curve can be estimated very efficiently with a linear approximation. So we just estimate these lines, basically. And to do that, we only need to learn two parameters, two coefficients. So we don't need to learn thousands and thousands of weights in a neural network. It's sufficient to just learn two parameters. And here you see three examples of such lines that we've estimated for three different nodes in the infrastructure. Here's also a sketch of the proof to why such a switching curve exists. This proof is due by Professor Vikram Krishnamurti, and it's a very elegant result in my opinion. So when we prove threshold structures over belief spaces, the main challenge is that, or I should say like this, it becomes very easy when you have a one-dimensional belief space, just a line between 0 and 1, because then all the beliefs are totally ordered, and then it's very easy to show that there must be some kind of a breakpoint where you switch from one action to another, and that is the threshold. But when you have a two-dimensional simplex, it's more tricky because now the beliefs have a partial order because you have basically two-dimensional vectors and they are partially ordered. So, but the idea behind this proof is that even in the two-dimensional case, you can form line segments that go from the corner here to the opposite side, which is this dashed lines here. And on each of those lines, we have total ordering of the beliefs. So that then we can show that on each of the lines, there exists a thresholding point, so that if you are on the line and you're above the threshold, then you should wait, and if you're above the threshold, then you should stop. Now, since we can fill the entire simplex with these lines, there exists an infinite number of these belief points here. And if you connect them together, you get a curve, and that is the switching curve. So here are the results when we directly estimate the this line instead of using deep reinforcement learning. So if you focus on the top row here, you see in red the performance of our method when we utilize this line structure or switching curve, and in purple you see the performance of PPO, deep reinforcement learning algorithm. So PPO works fine. I mean, it's also quite fast and it also converges. It's just that we can get even faster by utilizing the structure.
Finally, so we have seen now that we can solve and find best responses in the game very efficiently thanks to the decomposition and parallelization. But in the end, what we want to find is an equilibrium of the game. And to do that, we're going to use a very traditional approach called fictitious play, where we essentially iteratively compute best response strategies using the method we saw. And then we store those strategies in buffers and take the averages of those buffers. And those averages will, in the limit, converge towards an equilibrium point. So here are the results. You can focus here on the leftmost plot, which shows the exploitability metric. And that is essentially a distance metric to the equilibrium. As the exploitability gets smaller and smaller, we're getting closer and closer to the equilibrium. And if it is 0, that means that we have reached the exact equilibrium. What we can see from the plot is that we converge, but we do not converge exactly to the equilibrium. So we converge somewhere around like 0.24, I believe. So this is an approximate equilibrium. It's not an exact equilibrium. And I believe the reason why we don't converge exactly is due to that we use reinforcement learning. So here, this process is only guaranteed to converge to the equilibrium if we compute the exact best responses here. But in our case, we approximate the best responses with the stochastic approximation, or RL. And therefore, we get some insufficiency in the algorithm, and we don't converge exactly to the equilibrium. In the red curve, you see the performance of our method in the simulation environment, and in the blue curve, you see the performance in the digital twin. So recall this slide here of our framework, that we actually optimize our algorithm, or run the algorithm in the simulation environment, basically a Python code. And then every 10 minutes during this optimization, we extract the current strategies and we evaluate them in the digital twin by running them there. And that gives us those curves. And the fact that they are so correlated is sort of a empirical proof that the system identification step here is working good. It's actually capturing the important properties of the twin, and it takes that into account in the simulation environment, because otherwise we will not have this correlation. We also compared the convergence of our method against a state-of-the-art algorithm called NFSP, and so neural fictitious self-play. And NFSP does not converge at all, actually, in my experiments, and has much worse convergence than our algorithm. In fact, I tried several other algorithms as well, and I haven't yet to find any algorithm that converges unless you first decompose the game. So I would argue that decomposition is actually necessary to solve this game. Otherwise, it just becomes too difficult because your action space is simply too large. We're talking about thousands of actions if you don't decompose. So to conclude this long presentation, in my research, I work on a framework for automated security. This framework is centered around a digital twin and reinforcement learning. In our previous work, we have demonstrated that we can apply this framework to small-scale deployments and find the optimal defense strategies and outperform current response systems like Snort. The new thing in this work is that we present a decompositional approach, which can allow us to take this framework and also apply it to quite large-scale infrastructures. We have proven that the decomposition is optimal under certain assumptions, and we have shown that it reduces the computational complexity with several orders of magnitude. We have many ideas for improving this in future work. An obvious thing or direction is to look at different use cases. Here we looked at intrusion response, but one may also consider denial of service, APTs, or other security use cases. We also have some ideas for improving the solution framework, for example, using rollout-based techniques, and also by utilizing ideas from causal inference. So with that, I thank you very much for your attention and for listening to me. And if you have any questions about this work, please shoot me an email and I'm happy to answer. Thank you.